ahead and turn to chapter 10. Turn off the air so y'all can hear me. Chapter 10. Okay, so calculations for special populations. This is usually like your pediatric populations based on their weight and their age. Okay, so this one gets a little bit more detailed, so you guys need to make sure you pay attention and follow along really well. All right, so let's look at the words on page 331. So adolescence is considered 13 to 17 or 20. Usually, once you get above 12, most people can use the adult dose. So generally speaking, that's what you see. Body surface area. Okay, it says this is the means of calculating doses of medication on the basis of weight and height using a nomogram. So we'll look at that in just a little bit. Clark's rule, Freed's rule, and Young's rule are three things that are listed on here in the keywords. These are all formulas that we use in order to find the correct amount of medication. So Clark's rule, we find it from, we try to use the child's weight to figure out, using the adult dosage, how much they actually need. Freed's rule uses it's for an infant from an adult. And then Young's rule, you use the child's age to hopefully figure out what the dosage should be for the medicine. Okay, so this is not, these rules, like using these and figuring out the right dosage for medicine, is not really going to be a pharmacy tech job per se, but it is important that you understand how you get these medications, how you get these dosages, and you need to have an idea if something seems like it's way off, you know, what do you do? Infant is 1 month to a year. Neonate is birth to 1 month. And then a nomogram, like it says, is a graph or chart that shows a relationship between numerical values. So we're looking at height and weight and body surface area. So we'll look at those in a little bit. Okay, let's just get started. 344 is introduction. Says children are not small adults, but rather distinct individuals who have different medication absorption, distribution, metabolism, and excretion. Rates compared, excretion rates compared with adults. I'm sorry. The growth and development of the child, or the focus of the field of pediatrics, significantly affect the prescription for medication for the child. Pediatrics is very specialized. You can't just think of kids as just little adults and dose them that way or treat them that way. Some things have a major difference. Like some of the medicines that kids take for ADHD are actually for adults, are stimulants. Okay, so they have the opposite effect. With toxic medications such as chemo, even non-elderly adults with normal organ function may require the use of body surface area based on height and weight for drug calculations. So some more potent medicines, they may still use some of these rules, or at least a nomogram, to figure out the dosage, even though it's not necessarily for a child. Patients who have excessively low body weight or muscle mass, or those who are obese, may also require dose adjustments for some meds. Individuals with renal or liver dysfunction, whether adults or children, often also require dose adjustments. That's because, you know, some of your liver filters out a lot of this medicine, same thing with your kidneys. So they may have to change the dose for that reason. All right, look at the tech alert. It says, remember that if the manufacturer provides a pediatric dose or dosage for medication, then the dose or dosage indicated by the manufacturer should be used. So you don't use these rules and these formulas if they already have a formula or a dosage set in place for pediatric purposes. Okay, so if that happens, you use the manufacturers, you don't use these rules. All right, calculating medication doses by body weight. So one of the main conversions we're going to need to know in here is pounds to kilograms. And you guys need to know that anyway. Okay, so that's one you just need to memorize. There's 2.2 pounds in every kilogram. Okay, 2.2 pounds in every kilogram. That's one that you need to memorize. Find a better marker here. Okay. So let's look at this. Now I'm going to use, it shows you ratios again on here. I'm still going to use dimensional analysis because, again, it works for multiple problems. I think it's going to function a little bit better. So let's do some of these practice problems. Okay, number one, the child weighs 65 pounds. What is the weight in kilograms? Okay, we're wanting to know the weight in kilograms. 65 pounds. We know that in 1 kilogram, marker's not working. It's not working very well. I know you guys probably can't see that. Okay. So in every kilogram, we have 2.2 pounds. Okay. And we know that this kid weighs 65 pounds. So make sure I've done this correctly. Kilograms on top, so it's just 65 divided by 2.2. Okay, 65 divided by 2.2, and it's 29.5. 29.5 kilos. That's their weight. Okay, now one way to know if you've done this correctly. Kilograms are a lot bigger, a lot heavier weight than pounds. So if you're figuring out if you are trying to figure out kilograms, so you already know how many pounds they have, their kilograms is going to be less than what their pound was. It's actually going to be almost half. It should be right around half of what it is. So that's a good clue. Okay. Same thing with the other direction. If you've got kilograms and you're trying to figure out pounds, it's going to be more pounds than kilograms because it's 2.2 pounds in every kilogram. So it's almost twice as much or a little bit more than twice as much. So that's a good way to kind of check yourself. I'm not saying it's not exactly half or doubled, but that's a good way to kind of get an idea. Okay, does that make sense? 29.5 is, around half of 65. So that should clue you in. Let's look at the next one, number 2 on here. Okay. Number 2 says an infant weighs 8 pounds and 12 ounces. What is the weight in kilograms? Okay, so we know we want kilograms. And we know in every kilogram there's 2.2 pounds. Now, one thing that's different about this, 12 ounces is only a fraction of a pound. So you can't do 8.12 because there's not 100 ounces in every pound. There's 16 ounces in a pound. So that means their weight is actually 8 and 12/16. Okay, so that's the weight, 8 and 12/16, which is 8.75. Okay, so it's easier if you've got 8 pounds, 12 ounces, it'd be 8 and 12/16 to figure out that decimal. Okay, 8 12/16 is 0.75, so we know 8.75 pounds. Make sure you keep that in mind. Ounces are not, you can't just make it into a decimal. Okay. So 8.75 divided by 2.2 should get 4, I believe. But yeah, 3.97. So basically, you get 4 kilograms. Okay. So that's that. That's pretty straightforward. Now let's look at dosages. Okay, go on down to the bottom of 346, page 346. Because after you've calculated the pounds to kilograms, the next step is to place the number of kilograms into the expression milligram per kilogram. Using a physician's order for the strength of the medication to be given, you may find that the physician may place the number of times per day or amount per day that the medication is to be administered into the equation. So sometimes, like the doctor may prescribe a medicine and it may say 2 milligrams per kilogram per day or 1 milligram per kilogram per hour. Okay, so you'll see those are normal orders that the doctor might do, and then you have to work out how much you actually get. Okay, so the look at the tech note down there. It says the slash in the formula, milligram per kilogram per dose, or milligram per kilogram per times a day, is the same as having multiplication signs. So the formula would read milligrams times kilograms times the dose. That's how you can work it out if you need to get to that. And I'll show you how to put it on here, if you will. Okay. The other one says, in the formula, substitute the knowns of milligrams provided by the physician's order in kilograms that are calculated from the patient's weight, and then multiply as indicated. So this one's going to give you steps how to figure out milligrams per kilogram. Now this says you can just multiply, which you can. So look, obtain the weight of the patient and calculate that weight into kilograms. Read the physician's order for the strength or weight of the medication that is to be provided. Complete the calculation of medication in milligrams per kilogram by multiplying. And then after obtaining the dose of medication to be administered, use the ratio and proportion and dimensional analysis or formula method to calculate the dose, solid tablets, or capsules. So we can work out, we'll use this method to begin with, and then I'll kind of show you something else. Okay, so look at 10.1. A child who's been diagnosed with epilepsy weighs 53 pounds. Okay, the physician orders Dilantin 30 milligram capsules to be given at 2.5 milligrams per kilogram per dose. So our order is for 2.5 milligrams per kilogram per dose. Okay, and then we've got what's available is 30 milligrams capsules. Oh, but, well, caps. Okay? Now he's saying that, they're saying a couple things. One, because we've got milligrams per kilogram, they're saying that it says obtain the weight of the patient and calculate it into kilograms. So let's just do that first. We're going to follow their format here. Okay, so 53 pounds to kilograms. Okay, we'll just work this out. Every kilogram, we have 2.2 pounds, and then we've got 53 pounds up here. Okay, so 53 divided by 2.2. It's 24.1, so that's our kilograms. Okay. They're saying to get our dose, all we have to do, or step 2, it says, read the order, we already did that. 3, complete the calculation of milligrams per kilogram by multiplying. Okay, so we know that 2.5 milligrams times 24.1 kilograms is going to give us our dose. .5 milligrams per dose is what we end up with. They got 60.25. But anyway. Yeah, I didn't do that right. Now my calculator. So, anyway, we'll go with this. So 60.5 is our milligrams per dose. And we know that 60.5, okay, so if our tablets come in 30 milligrams, and we have 60.5 divided by 30 milligrams, it's going to give us 2. It's going to be close enough to 2 tablets for that to work. So we know that the dose to be given is 2 caps. 2 capsules will pretty much equal 60 milligrams. Okay? Now, the other way I'm going to show you how to do this, this formula is great. You can see it worked out perfectly. Okay, the other option is to do dimensional analysis with all of your info. Okay, so I want to know how many capsules we actually need. I'm going to make my dimensional analysis really long. I'm going to put it all into one equation. Again, you can work it out just by these steps if that's the easiest for you, and that is perfectly fine. I'm just showing you guys a different way to do this. So I know right now, I know that in every one capsule, I have 30 milligrams. Now, whenever I put something like this into my dimensional analysis, this milligrams per kilogram per dose, I always do, you can, like we've got dose on here, you really don't even need that because our dose, it's really caps per dose is what we're doing at the end. So you can leave that if you want to, however that works for you is fine. But you can put that kilograms and dose on the bottom. So I could put 2.5 milligrams per kilogram per dose down here. Or we can just take off the dose for this particular problem, but we'll just leave it since I wrote it down here. Okay, we want caps, but now we've got kilograms down here we've got to get rid of. So I know that in every kilogram we have 2.2 pounds, and there's 53 pounds. Okay, make sure I cross out all of my units that can be crossed out from top to bottom. I end up with capsules over dose, which is what I wanted. And then I can actually multiply, just multiply straight across. I can get my calculator to work. It's not working right now. Yeah. Okay, so if I multiply straight across, 53 times 2.5 divided by 2.2 divided by 30 gives me 2. Okay, so that's how you can do this in one big step. This is why I use dimensional analysis. Now, I'm perfectly fine with you using that other step. If that helps you keep it straight to do kilograms, then do dose, then do capsules, that is perfectly fine. Or you can do dimensional analysis with the whole thing. Okay? It's going to give you the same answer. All right, let's do oh, they did a big long dimensional analysis on page 349. You can see that one. Okay, let's just keep on going. Hopefully, you guys, that one is pretty straightforward. Okay, the use of Clark's rule for pediatric dosage on 349. Since other method used for calculating pediatric dosage based on their weight or mass is Clark's rule, although you may never use the following means of calculating a pediatric dose of medicine, you should be familiar with its indications. With Clark's rule, as with others for children's dosages, the assumption is that the average adult weighs approximately 150 pounds and that the adult dose is indicated by the manufacturer is calculated on that weight. These days, you know, our average weight is higher than 150, so they're like kind of rethinking all of this. Thus, Clark's rule is being phased out because of that reason. Again, if a child's dose is indicated by the manufacturer, like on the info, then that's what you need to use. So look at Clark's rule. We'll write it up here, and you can put it on your formula chart. Okay, that might be a good idea. So it's their weight in pounds divided by 150 times the adult dose. Okay, that's how you figure it out. So in this, let's look at, let's just go ahead and do a practice problem and we'll look at these. Okay, 351, number 1, it says a physician orders VTID 10 milligrams per kilogram Q 8 hours for a child who weighs 55 pounds. I'm going to write down my info, 55 pounds. The medication, let's see, the order is for 10 milligrams per kilogram Q 8 hours. Okay, which if you guys will think, every 8 hours is actually TID. It's 3 times a day, 24 divided by 8. I'm all right, TID over here, so I'll know. Okay, and then the medication dosage, what's available is 250 milligrams per 5 milliliters. So in every 5 milliliters of medication, we have 250 milligrams. Now it says, what is the dosage strength for the child for the whole day? Okay, so for the whole day, what do we want? How many milligrams can they have for the whole day? So let's think about this. I'm going to use dimensional analysis. Actually, let's just go through, you guys, we'll do both again. Let's go through our rules like we did a while ago. Okay, so look, back on 347. Number 1, the weight and calculated into kilograms. So let's do that first. 55 pounds ends up being, let's do our kilograms. Every kilogram, we have 2.2 pounds, and we have 55 pounds. So 55 divided by 2.2, 25 kilograms. So that's our weight. Okay. The medication dosage is for 250 milligrams. I'm sorry, the whole day. So that's it. So now let's figure out, it said step 2 is to read the order. We did that. 3, complete the calculation, milligrams per kilogram by multiplying. Okay, now we want for the whole day, but let's go ahead and do this. So 25 kilograms, we know they have 10 milligrams times 25 kilograms. And this gives us how much they're supposed to have every 8 hours. Okay, but what we know is that if they have that medicine every 8 hours and we're wanting to know how much they need in a day, well, let's figure this out first, I guess, since that's one of the next question. So 10 milligrams times 25 kilograms is going to be 250 milligrams. Okay? Oops. Yeah, that's why I like dimensional analysis, otherwise I'm afraid I'm going to get something wrong. So 10 milligrams times 25, that's going to give us 250 milligrams. That's our amount per dose. So every 8 hours, they're supposed to get 250 milligrams. Okay, well, we know that if they get this every 8 hours, that means they're going to get that dose 3 times a day. So the question says for the whole day. So we're going to multiply 250 times 3. Okay, which is, I should know this, 750. Okay, so 750 milligrams is how much they're going to get for the whole day. That's how we figured that out. Okay, it's 3 times a day. That means they're going to get 750 milligrams. That's the answer to that first blank. Second blank says, what's the strength of medication for a dose? We already figured that out. It was 250. And now it says what volume should be given with each dose. Okay, what volume should be given with each dose? Our dose is 250 milligrams. Well, this one's easy. We don't have to work it out. But look, we've got 250 milligrams and 5 milliliters. So we know that 5 milliliters is the answer. Okay? But let's just say I didn't know that and wanted to do dimensional analysis for the whole thing. Okay? I can do that for, let's say, all the way down to each dose. So the amount of medication with each dose. So volume. I can put my milliliters over here. That's what I'm wanting to know. And remember, I always kind of go backwards to start with my milliliters on top, so I want to make sure that's what ends up over here. So I know the only thing up here that I've got for milliliters is this 5, so 5 milliliters. There's 250 milligrams in that. I know that there's 10 milligrams for every kilogram. Also, my milligrams here. I know that, let's say if I didn't know my weight already, I know that if I use my conversion factors, every kilogram has 2.2 pounds. I know that our kid weighs 55 pounds. Okay, and we get there. That's going to give us. That's going to give us our milliliters, how much they need per dose. Okay. should be should be 5. So 5 milliliters is what we would end up with. Granted, we already knew that up here. But anyway, so that's how that can function in dimensional analysis. It's all, you can work it out as all one big step. Okay? All right, let's do one where we have to use Clark's rule here. All right, let's look at number 4 on page 353. It says a physician orders Benylin syrup for a child weighing 30 pounds. Okay. Okay, so 30 pounds. The normal adult dose is 20 milligrams every 6 hours. So the adult dose is 20 milligrams Q 6 hours, or how many times a day? If it's 6 hours, 24 divided by 6 is 4. So that's QID, 4 times a day. Okay, the medication on hand is Benylin syrup, 15 milligrams per 5 milliliters. So that's what's available. 15 milligrams per 5 milliliters. That's all it goes. Okay, so now, what is the dose strength for this child? So how much do they need? How much do they actually need per dose? How many milligrams do they need per dose? Okay, and we got to figure that out. We're going to use Clark's rule because that's what we have. We have their weight and we have the adult dose. So that's Clark's rule is going to be our best bet with that. Okay, so if I follow Clark's rule, I know that I put their weight in pounds. So 30 over 150 times the adult dose. So one dose of this is 20 milligrams. And this is pretty straightforward. Oopsie. 5. Okay, so this is 5, 1 over 5 times 20. This is going to be 4 milliliters. I'm sorry. Oh, yeah. Sorry. So 4 milligrams is our dose. Sorry, I didn't do the math in my head again. Okay, so 4 milligrams is our dose strength. Okay, we got that. We know how much, that's how much they need per dose. Now it says, what is the volume of each dose to be given in the metric system? So we want milliliters. So now we know the order is for 4 milligrams. That equals 1 dose. Okay, I'm just going to write that up there for my notes. Now we want to know milliliters, the volume. Okay, so I'm going to put my dosage strength, or not my dosage, my medication strength that's available. And every 5 milliliters, we have 15 milligrams of medicine, and we need 4 milligrams per dose. So cross out my milligrams, I've got milliliters, that's right. 4 times 5 is 20 over 15. You're going to have 0.75 milliliters is what they're going to need. Okay. Am I crazy? Oh my gosh, I am crazy. Sorry, I inverted that, didn't I? I inverted my 15 over 20 instead of 20 over 15. 1.3. 1.3 milligrams. I'm sorry about that. Okay, so 1.3 milligrams. Oh my goodness, I'm still getting it wrong. I'm sorry. Milliliters, looking for volume there. So 1.3 milliliters is how much that we're going to get. There we go. Okay, I'm sorry. 1.3 milliliters. Okay, now it says, what is the volume of each dose in household measurements? Well, actually, if you look on this syringe, on the picture right there, it's really easy to see that. So look, if you do 1 1.3 milliliters, it actually comes right at a quarter or a fourth of a teaspoon. So that's pretty easy to see there. If you didn't want to figure that out, if you need to figure it out by dimensional analysis, you would put teaspoons over here. You know that in every teaspoon you have 5 milliliters, and multiply that by your 1.3. So 1.3 divided by 5, 1.3 divided by 5 is 0.26. So yeah, it'd be 1/4 of a teaspoon. Okay. Now, if I want to figure out how much they were going to need in a day, okay, then I would do my 4 milligrams times 4. So 16 milligrams because it's QID. All right, let's keep going. All right, look at page 359. So that we are 359. Okay, third method of drug calculations using body weight is BSA. BSA is based on weight compared to height of the person. This form of calculation is often used for pediatric patients, but it may also be used when preparing toxic meds such as chemotherapeutic for agents or for adult medication amounts for the elderly who are not of height or weight to be classified as the average adult. This calculation provides the most accurate determination of the therapeutic dose to be administered on the basis of body weight and height. BSA refers to the total body area that is exposed to the environment and is expressed in square meters. To calculate the BSA or meters squared, the weight and height of the person must be measured and then used for the calculations. The measurements may be accomplished either in the metric or English systems for use with a nomogram, a means of using a chart to plot height and weight and to provide the estimated square meters of body surface area. The children's nomogram is seen in figure 10.1. A nomogram specific for adults is also available for use with adults who fall outside what is considered normal weight or height for those who are being administered toxic meds. The nomogram to be used is based on the person's age or on the nomogram's limitation by height and weight. To use a nomogram, find the height and weight on the correct indication line of the chart. And notice that the metric system is on the left, height is on the right, and you can turn it over while I'm reading this if you want to look at it. They're on the next page. After finding the height and weight for either the child or the adult, draw a straight line between the 2 points to find the line where the straight line intersects the surface area line. The estimated BSA is the point where the line intersects the surface area meter squared line. For the child who is of normal height and weight for age, the BSA may be calculated only by their weight. Notice that the nomogram has added this column with the center box that shows the BSA indicated by weight in pounds for the child of normal height and weight. It's not found on the adult one. So let me show you real quick how to find this. I'm going to show you this. So look at these practice problems. So using the proper nomogram, calculate the BSA. This says a child weighs 15 pounds and is 24 inches tall. So what you're going to do, 24 pounds and, where did I say? 15 pounds and 24 inches. Okay, so what you're going to do on here is I'm going to look up their inches on this side, 24 inches. Okay, I'm going to put my line there. And we're going to ignore this boxed column for now. 24 there, and then they're 15 pounds. So the weight in pounds is right here. And I'm going to put this on that 15-pound line. There it is. 24 and 15. Okay, and I'm going to look here, and look at this line that has S surface area on it, and that's what I'm going to look at. So looks like it's like 3.6 is what I would say. 3.6. Okay, so that's how you find body surface area using this nomogram. That's all you do is just to draw a line between those two and then find the surface area on that chart. Now, if you have, notice number 4 says a child is a normal height for 40 pounds. That means if their average height for their weight, okay, then you can use this box in the middle. And if you look on here, it just has their weight. So their weight in pounds is 40. Here's 40. So their body, their surface area. Sorry, I was looking at this upside down a while ago. The other one was not 3.6, it was 0.36. Anyway, so their body surface area over here, if we look up 40 pounds, they're going to end up being about 0.75, it looks like. Okay, so that's all you do on these. That's how you find body surface area on this nomogram. And if you'll notice, the adult one is on the next page, on page 361, and you do the same thing with the adult one. The only difference is that the adult one doesn't have that normal box in it. And that's it. Okay, so we won't have to necessarily figure all that, but let's look at this. So look at 359. It says, after the BSA has been found, the following formula is used to calculate the dose of medication. The typical body surface area for an adult is 1.7 meters squared. Therefore, this number is used in the formula to calculate doses for children. So here's the formula. Okay, here's the body surface area formula. Okay, the desired dose is the body surface area. Oh, wrong marker again. Okay, we have the body surface area divided by 1.7. Okay, times the adult dose. Okay, so that's how we figure this one out. That's the formula whenever we're using body surface area. Okay, so if you run across a question and they give you height and weight, then you can use the body surface area equation to figure out a dosage. Okay, if you only have the weight, then you can use Clark's rule. If they say their normal height, they're like 40 pounds and their normal height for their age, then you can use that normal chart on that nomogram. And I'll put a little sticky note or something on here so you can go back to it whenever you start to do the post-test. All right, let's do a couple of practice questions on here too. And it goes over 362. If you get confused again, it goes over how to read that body surface area. Wait, did I miss a rule? No. Okay. So these are going to use body surface area. Let's just do number one. Says a child is 25 inches long and weighs 15 pounds. The physician orders Lanoxin elixir daily. The adult dose of Lanoxin is 0.25 milligrams per day. The available medication is Lanoxin pediatric elixir, 0.5 milligrams per milliliter. Okay, so let's just write down our info that we have. We have their height, their 25 inches height, and their weight is 15 pounds. So we can figure out their BSA from that. Let's go ahead and do that. If you go over here there's one on this page too, on page 362. Okay, if you draw a line between the 25 inches and 15 pounds, okay, you're going to get 0.3. You're going to get 0.36 again. Someone we just looked up. Anyway, so that's 0.36. Okay, so now let's write down the rest of our info. So the adult dose is 0.25 milligrams per day. Okay, and then the available medication is 0.05 milligrams per milliliter. Oh, that's doesn't take much. Pretty potent. So indicate the BSA calculation. We already did that, 0.36. What's the daily dose strength of Lanoxin for the child? So we want to know how much are they really supposed to have. So we already have the body surface area, so let's use the body surface area formula. So we know their BSA is 0.36. Put that over 1.7 times the adult dose, which is 0.25. So that's what we're wanting to know. And then you just multiply, divide that out. 0.05 milligrams. That's how much they need. Now it says what volume of medication would be administered. Okay, if we go up here, we know what's available is 0.05 milligrams per milliliter. So we know they're going to get 1 milliliter. It's the same thing there. If not, then you use your dimensional analysis to figure out their volume. Remember, is your milliliters or teaspoons or whatever. Okay. So that's how you use the BSA. So make sure that, again, it's going to tell you how to use that. Okay, let's look at page 368 and go over these last couple of rules. And then we'll be done. You can work on the problems. Okay, it says pediatric dosage may also be calculated by age using Freed's and Young's rules based on the normal adult dose. Freed's rule is used for an infant up to 12 months based on the age in months times the adult dose divided by 150. Young's rule is used to calculate medications for children from 1 to 12 years based on their age. Okay, so let's write down these rules. So Freed's, and I put these on your formula chart. Look, age in months times the adult dose divided by 150. Okay, Young's rule is age in years times the adult dose divided by age in years plus 12. Now, don't forget your order of operations. Okay, your order of operations. You're going to add your age in years plus 12 first to that. So make sure you don't mess that up and do that at the very end. All right, let's do a couple of practice problems in here. Number 1, physician orders milk and magnesia for a 3-year-old child. The adult dose for milk and magnesia is 30 milliliters. So what volume do we give? Okay, so look, 3-year-old, the adult dose is 30 milliliters. So what volume? All we have is their age in years. So we're going to use Young's. Okay, think Young is age. Anyway. Okay, so their age in years is 3. The adult dose is 30 milliliters divided by their age in years, 3 plus 12, okay, which is 15. So 3 times 30, so I've got 90 divided by 15, which is, what, 6? So 6 milliliters would be their dose, right? Yep, 6. Okay. All right, let's do one more. Okay. Number 2, a physician wants a 6-month-old child to have phenobarb. The usual adult dose is phenobarb 30 milligrams. Medication is available in an elixir of 20 milligrams per 5 milliliters. So 20 milligrams per 5 mils is what's available. We know that they're 6 months old. So if they're months old, then we're going to use Freed's rule. And the usual adult dose is 30 milligrams. So we're going to use Freed's rule. So age in months is 6 times the adult dose, which is 30 milligrams, divided by 150. This is going to tell us how many milligrams they actually need. which is going to be sorry. .2 milligrams. Okay, how many milligrams they need. Now look, it's want to know what volumes. We're going to go back and use dimensional analysis. So we already know what's available. We want to know how many milliliters they actually need. So we've got 5 milliliters to 20 milligrams in that. And then they need 1.2 milligrams is all that they need. And you just use your dimensional analysis. So 1.2 times 5 divided by 20. 0.3 milliliters. Okay, 0.3 milliliters. Okay, so that's how you're going to use those two. And that is it. So you're going to have to really pay attention to what information. I would write all these formulas on an index card or write it on your formula chart so that you got them to use, and you can figure out whenever you go through these questions on here, you're going to need to figure out which formula to use on which question. You may have to go back and use the nomogram. Okay. Let's just do the same thing on this one. Let's do the odd questions. On here, you guys can figure those, get those done, and we will we'll be done for today. So I hope that this is clear. I know this is kind of a lot, so make sure you write that down. I am fine with you guys writing down these formulas on an index card and using that whenever we get to the test. And that's perfectly fine with me. Anyways, but that's that. Okay, so we'll be done